differential phase calibration using a single 4x8 MIMO equalizer. We understand that in our in-phase and quadrature phase branches in our coherent receiver or at the transmitter, we are suffering from imbalance. So even we compensate the S21 magnitude response, what we left is the IQ common phase and IQ differential phase. So in this presentation, I will talk about how to calibrate this IQ differential phase more accurately. If we are lucky, when we just plot out the differential phase between I and Q, we may just have some ripples across the frequency. And we can just do a linear fit and obtain the slope. So this slope infers the value of the skew. But unfortunately, in the next generation coherent technology, we are limited by the electrical responses, and most likely you will see a large variation of differential phase across the frequency. So since we will do a curve fitting, the frequency range that we use will actually induce the error because we see a lot of fluctuation. So it is very, very important to estimate correctly and compensate this frequency-dependent differential phase. There have been several existing methods to do that. So usually we will separately compensate and estimate the transmitter and receiver response using a two-stage MIMO equalizers. For example, for the receiver impairment, we will use the CMA-based, for example, 2x4 complex MIMO or 4x4 real MIMO. While for the transmitter side, we'll use a 2x2 real MIMO per polarization. And there has been a paper from OFC 2019 from NTT that mentioning we can use a single stage 2x8 MIMO equalizer to compensate both transmitter and receiver impairment. However, the principle in this paper is not well explained. We don't know how to extract the transmitter and receiver impairment at the same time. So back to the calibration. In this presentation, we are talking about the calibration. We will still use the currently existing method to estimate the impairment from the devices. So since we know the data, we will turn all the blind approach, like a CMA-based approach, to be data assisted by using a reference that is rotated by the frequency offset, so that we can enhance the calibration quality. And the goal of this paper is to design a single stage equalizer so that we can jointly compensate and estimate the transmitter and receiver IQ differential phase responses. So here is our work. And please note that all these approaches, including this work, require non-zero frequency offset because we have to separate the transmitter from the receiver impairment. Here shows conceptually our proposed method. The first one here, this is a physical channel. We understand that our DSP has to compensate or undo log-wise these impairments in a reverse order. For the previous 2x4 or 4x4 equalizer, for jointly compensate the receiver and also to do the demultiplexing, we have to shift the CD compensation before the DSP, all the DSP stages. So, and also we have to multiply each of the ADC branches using a CD compensation phaser so that we can avoid the IQ mixing. For the NTT approach, we will do one more step, which is to shift the frequency offset compensation to the end of the DSP so that we can combine the middle three blocks together. And also we have to make use of the complex conjugate of the inputs. And in this paper, we are going to shift the frequency offset compensation in front of the CD compensation so that we can respect the ordering between the frequency offset compensation and CD compensation. And also for this work, we are doing factory calibration. We'll set CD to be 0. For details, first, at the ADC output, we will transform these ADC outputs to another 4 ADC outputs, but which is a complex value. We'll compensate the frequency offset using spacer, and also multiply the quadrature parts of the 4-channel with the imaginary constant J, so that now we have 4 complex valued sequences, and we'll duplicate them to their complex conjugate altogether with 8 inputs. And these 8 inputs will convolute in time domain with a filter bank, which is 4x8 equalizers, and each of the coefficients consists of 75 FIR tabs. We are not going to talk about the optimization process because it should be well known to us. And our goal now is to get a combination of these filter coefficients so that we can jointly estimate the transmitter and receiver differential phases. So here, just state our proposed method. I'm not going to explain everything here. So please note that there's no unique way to get the combinations. You can generate your own combinations, but the above are just justified based on our observation, based on the channel inverses or the device parameters, and also based on our experimental results. To verify first the transmitter IQ differential phase extraction, we'll just do a direct loop back within our transceiver module, which is a back-to-back setup. And first we load some funny shape, for example, a sinusoidal differential phase on the back, and we can successfully retrieve this phase from our DSP using our method. And we also try to do the skew measurement. For example, we introduce some skew at the transmitter and also add some skew at the receiver to see its impact on the phase extraction. So here shows our result. And first we ignore the result, which is in black because the standard DSP was obsolete. We are not going to talk about that. And our results are shown like those red curves. And we see that our result aligns with other methods actually, and also is pretty unbiased, except that when we increase the receiver skew, we see a higher standard deviation. But still, this we can see a large standard deviation, but it is still within 0.1 picosecond over 30 random SOPs. We are very interested in why we will see a standard deviation which is higher than other methods. So we will pick the extreme case, which is at -3 picosecond transmitter skew, and go back to see its differential phase. And basically, we see our result, which are the red curves, aligned with other existing methods, except at the high frequency edges, at the signal band edges. And to explain this, why we just plug all the channel parameters or device parameters back to the combination that we chose. Then we see there's an interaction between the receiver phase responses and the APCD, which is the polarization parameters. So that's a solution to reduce this fluctuation when estimate the skew, which is we'll just ignore the signal band edge. We do the linear fit perhaps just up to -35 to the positive 35 gigahertz. Then we measure the receiver differential phase using a method. It shows that our method, which is 4x8 complex MIMO, is very robust to random SOPs. So you see a lot of curves in each plot, and each curve represents a random SOP. And for the 4x4 real MIMO or 2x4 complex MIMO, the existing approach will have a larger fluctuation. And this problem will be more serious if the transmitter impairment kicks in. So So to understand why he would like to just address this issue because for the existing method, we may use ideal reference. We assume that ideal reference should be used to reduce the fluctuation caused by the existing method. We may also need to add the transmitter impairment in the references. And also to explain why our method is so robust, we also plug in all the channel parameters and also device parameters into the filter coefficients that we chose. And we can see there is no transmitter phase response interacting with ABCD, which is the polarizing parameter. So finally, we will summarize using the standard deviation by comparing with other approaches. We can see that other existing approach will have a higher standard deviation measurement error. Compared to them, our approach will show actually is more robust to random SOPs to give you a less error and also independent of the transmitter skew. So finally, we also compare the two approach, which is we can either compensate the receiver skew or compensate the entire profile of the differential phase and frequency domain at the receiver. We can see by doing the latter, we can see a better performance. So it is very important to compensate the entire frequency profile of the differential phase. To summarize this presentation, first we proposed a single stage 4x8 MIMO equalizer to jointly compensate and calibrate transmitter and receiver differential phase. And the principle is to extract the differential phases from the equalizer coefficients. We ran an experiment, which is 96 gigavolts dual pole 16 coulomb single carrier system. The sample size to generate our statistic is 30 random SOPs. We can see that for the transmitter differential phase, we can see higher fluctuation at the signal band edge, but we can reduce it by just ignore these fluctuations at the high frequency. And for the receiver differential phase, we can see that our method is super robust compared to other existing methods. And so altogether for the skew measurement, our accuracy is pretty good. The error is still below 0.1 picosecond standard deviation. And finally, we would like to acknowledge the experimental validation offered from the production team in Huawei Technology from Guangdong, China, from March to June last year. So that's all for my presentation. I will take the questions from you.
Yeah, Dr. Chow, thank you for the very nice